Good evening, everyone. This video here, what I'm going to do is look at the reception with the DSP filter in, the two Hilbert transforms. I'm going to divide this into a couple of segments. So for a start, the next segment of the video will look at some on-ear reception, just literally half an hour ago on 80 meters. We'll then look to do some test transmissions using our second radio here and compare what's being received on the Teensy versus our commercial rig. So we'll transmit from this rig here and we'll look at the differences between those two rigs. Now in the video I talked about changing the bandwidth on the Teensy. I misspoke in there. It wasn't a 2.8 kilohertz filter initially. It was 2.7, and then we looked at bringing that down to 2.4, so just a little bit less. So just a little bit confusion there, unfortunately. Sorry about that. Got a bit tongue-tied as I was talking. So what I'll do here is I'll just break, and the next segment we'll look at some on-ear receptions, then some tests, and then at the very end of the video it looks at the design software and then sucking that, all those coefficients that were designed into the program and then into the Teensy. So just hold fire there and we'll continue.
She's going to hit you in the pocket one way or another to get her money, and now she's talking.
Okay, so that's with a 2.8 kilohertz filter with the bandwidth of the Hilbert. Just a bit of fading there. So that's the Teensy, and then we'll have a look at the commercial radio. Turn that volume down. We'll come up to here. So this one here has 2.4 kilohertz, so it's a lot narrower. Very shortly I'm going to upload into the Teensy a narrower bandwidth Hilbert, and we'll see how that sounds. So back down to the Teensy.
It's still no good profession down there. They must not be the first.
That's below.
Got a grey leg.
And then above.
Back to where they were.
Right. So let's just put in
meal places and things like
a different filter, and we'll record that.
Where a rat poked its head over the edge and it jumped.
Right. So that's now with a narrower bandwidth Hilbert transform.
And it leapt through the air like a bullet. And I reckon it went 15 or 20 feet into the boysenberry. I could see it from its nose right to the tip of it. It was a straight line like a bullet.
So I don't record too much because that guy's obviously not aware that I'm recording him, but that doesn't sound too bad. So what we'll do now is we'll just do a test transmission using a separate transceiver. Excuse me for leaning over there. And we'll just see how that sounds. So let's just get a little MP3 player here, and what we'll do is, so that's the power supply fan turning on and off. So we'll just plug in a little MP3 player. We'll turn that on. And we'll choose, let's see if that's free. We might go down to, yeah, let's go down to 760. And we'll key that. That's free. That's transmitting into a dummy load, so it's not going out on the air. Right. So that's coming up. Okay, so that's our commercial rig picking it up. And we'll come down to the Teensy. So we've still got the HF antenna plugged in there, so we've got the atmospheric noise coming in, and the sensitivity of the radio is enough to pick up that dummy load.
Hi, this is Caroline calling from Toronto, Ontario, Canada.
And back up to the commercial rig.
Supported by Tranquilize. Need to send money internationally? I knew the transfer switch would fall for a bad exchange rate.
Now this one here is currently hooked up to a 20 metre antenna, whereas the bottom radio, the Teensy, is currently plugged into an 80 metre antenna, so just a little bit different there with the atmospheric noise levels coming in. Right, so that's picking up lower sideband. What we'll do is we'll change our transmitter to upper sideband, leaving the receiver on lower sideband. So you can just hear there on the commercial rig, just a little bit of the, it's back to lower sideband, just a little bit coming through there. So let's turn the volume down on that one, and we'll go back to lower sideband, and we'll turn up the Teensy.
I truly do not even remember like writing. Why is the moon devoid of all color?
And we'll go to, so again just a little bit there.
Or is that just the coincidence? That we zeroed in on one of Scott Clutch's bits.
So what we might want to do there is just play around with the gains subtly on the input to the Teensy, which we can do, just to offset any potential imbalances between the outputs of the two NE612s. So that's very easy to do. We can adjust the gain there. At the moment you would have seen or recalled from the software that the gain coming in is currently set on 1. And 1 for lower sideband, and then 1 and -1, so basically full gain. So we can easily change it down to say 0.95 or 0.98 on either one to get that balanced a little bit better. But that's actually not too bad. That sounds pretty good. So what we'll do now, let's just have a quick break, and then we'll bring up the Iowa Hills designing or the filter design software, just to get a bit of an idea of how to use that to generate the coefficients, and then we'll just have a little quick look at the Teensy code, just to show that being put into the code, and that'll do, I think, for this video here.
Your title has got to be the coolest title of anyone I've ever interviewed.
My title is the coolest title, the commander of the East.
But that's not too bad. Okay, let's pause there, and we'll bring up the design software. Rightio, this is the Iowa Hills filter design software. This particular one is for, like I say, the Hilbert. I've also got the fur one. All of these are freely available from the Iowa Hills website. If you go to the download page, you'll see them there. Alright, so there's a few things we need to set up to design our filter, and then to ultimately generate, as you can see here on the right hand side, a whole series of coefficients that we use to basically set up that digital filter within the Teensy. So if we go to the design, the audio shield design page for the Teensy, it talks about if you want to generate these coefficients for the filters, whatever software you're using, you need to set the sampling frequency to 44117. So I've entered that under sampling frequency there, and then we get to sort of play around with some frequency, the center frequency, and some bandwidth, and the number of taps. And down here we'll be looking at what the overall pass band of the filter looks like. The Hilbert is a band pass filter, and the other thing we want to do too here is we want to go to band pass phase added, which now enables this selection here. So here we can input our plus 45 for the first filter, and then for the second one we'll keep all the other settings the same, but we'll bring that down and we'll make it a minus 45 degrees. So we can make that, and that gives us that matched pair that we'll be using for in the Teensy. So anyway, so like I say, sampling frequency 44117, our center frequency. So what we're going to do there is we're going to just use a little bit of an assumption here. So the audio that's been passed to our Teensy is ranging, it's been brought down to DC in the two NE612s, so the audio bandwidth for speech is roughly 300 Hz through to 3 kilohertz is what we're after. So that's what our bandwidth is going to be here. So I'm going to set this we'll go for 2.4 kilohertz. So we can change that, so that's 2.43, we can fine tune that, and we can bring that down to 2.4 kilohertz. So that's changed the bandwidth at the -3 dB points, and it's still centered around 11 kilohertz. So we can see here right down the middle, roughly 11 kilohertz. So I want to now bring that down to be around our audio that's coming into the Teensy. So like I say, it's ranging from roughly 300 Hz to 3 kilohertz. So the middle of that range is 300 plus 3 kilohertz minus 300 divided by 2, which turns out to be 1650 Hz. So I now want to basically reduce this and get our center frequency to be 1.65. So let's fine tune that. So 1.65 kilohertz is now our center frequency with a bandwidth of 2.4. So that should roughly be coming, or allowing, with our -3 dB points, that's sort of roughly 300 to 2.4. So basically, what's that, 2.7? So that's what we'll do for setting up this particular filter here. Now, the number of taps will have an effect on the sharpness of the skirts and our passband ripple. So you can see here as we increase, you can see it having a change there. Now, what I'm going to do is I'm going to put it back to roughly 70, and I'm going to add in a window. So a Kaiser window we're going to use. A lot of the documentation for the design of these sorts of filters talk about the use of a Kaiser window as being quite a good choice. And you can see there with the window off and the window on, there's quite an appreciable difference there in our stop band. So at the moment it's starting down there in terms of the ripple at roughly -75 dB. And if I turn that off, it sort of leaps back up to that sort of -45 region. So per a lot of the textbooks, I'm going to leave that Kaiser window on, and I was going to leave it as a default of a Kaiser beta of 50. I'm also going to leave the raised cosine at 0.85. Now, I've said this many times in these videos, I'm not an expert in this area. I did some DSP many moons ago, but this was pretty well a default, and I'm going to leave it as a default. If somebody else wishes to play around with this circuit and wants to do their own thing, feel free to have a good old play. And you can see there's some, as you change that, there's some differences in terms of the bandwidth and then the roll-off rates. If you go beyond that, it starts to grow again. So I'm just going to leave it the default of 0.85. So just double checking, 44117 sampling frequency. We've got our center frequency where we want it. We've got our bandwidth to be what we want. I'm going to just stick with 70. So 70, say 59, sort of gets to about 70, and not really much change after that. So rather than sort of try and make this too computationally difficult for the Teensy, I'm just going to leave it at 70 taps. So that will generate 70 coefficients. So just double checking, -45, we've got that correct, and we can now go calculate. And that's now created for us a nice set of coefficients. And what we can do for that is we can go File, Save Coefficients, and that's now saved it. And this is going to be, I'll just append that with -45, just to align with our -45 phase add, and save. And straight away I'll just nip up there, and I guess I could have typed it in, but we'll go the slow boat and we'll bring that up to 45. 45, calculate, file, save coefficients, and we'll just make that plus. So that's now created for us our 2 text files full of coefficients. So we can close that program down now. Let's go to documents. One day. Let's have a good think. Not responding. Very interesting. What's going on there? It's never a good look. Right, back to documents. So what we've got here, my son wrote up a quick Python script to convert these coefficients into a format which can be easily placed into our Teensy program. So just a matter of, I'll just take that name, control copy, we run the formatter, it asks for the name of the input file, there it goes there, and it's now created an output file, and that output file has now basically just reformatted that original number. It's put a couple of brackets around it, it's multiplied it by 32768 and made it a short, and that's what we'll use to place into our Teensy program. So just bringing that program up, programming Teensy SDR 2018. Let's go with, we see this was 2400, and we'll just have a look at that. That's the one that we were just demoed before. So that's the sketch open, and you will recall from the previous video that there's these 2 areas here which we were defining the matrix for, or the array I should say, for those Hilbert transforms were empty, and now you can see we've now placed in there what was generated with that text file. Closed off. There goes the minus 45 one, so that comes out of that second text file, or the first one in this particular case. And that's it. That's all we have to do to now make this program work. So then it's just a matter of compiling it and then sucking it in. So down here, when we saw before, when it goes to start, when we turn on our receiver and it starts these 2 filters, dot begin, it runs away, it gets those coefficients from that an array up the top, and it's also given the number of Hilbert coefficients. So if we just race back up the top again, we'll see here that we defined number of Hilbert coefficients to be 70. So that aligns with the 70 taps that we selected in that Hilbert transform software from Iowa Hills. And that's it. So that's all I'm going to do for this particular video. Like I say, now it's just a matter of playing around with different settings on that design software in terms of fine-tuning the unwanted sideband, in terms of any potential differences in the amplitude of the audio coming in. A lot of commercial software has the ability to correct for that. Some of it's automatic, some of it's manual, but for us, if we were to do that, we would do that down here when we turn on our receiver and we set up our summer. So here we got here the gain settings. So for input 0, we've got here a positive 1. If we decided that the gain or the level coming in on input 0 was larger than the one coming in on input 1, then we could make that say 0.95. And we'll do the same thing down here. So that's just a way that we can, on the fly, modify the gain of that summer and therefore offset any differences we may have. So I'm not going to do that right now, so I'll just leave that sort of defaulted on 1. So I think that's all. I won't talk anymore, and we will work out where we want to go to next. What I'll probably do, rather than sort of labouring at this stage any more different architecture changes to the digital side of the radio, we can certainly do that maybe at the end of the series, but what I vote we do now is move to transmit. So I probably won't talk about that now, because we will have to make some changes to the software to bring that microphone audio in, create our or to basically to do our modulation, and then to set ourselves up for a phasing method for the SSB modulation or transmission. So let's not talk about that now, we can do that in a later video, and we'll go from there. Any questions, sing out, otherwise I'll say 73s, and we'll see you next time.